Good afternoon. I am Theresa Stack, an associate professor at Montana Tech, and this learning unit is the second part of exposure assessment, and it will cover unusual work schedules, and that is when we make an adjustment to the occupational exposure limit to account for those unusual work schedules. And then we'll also take a look at evaluating exposures when there's additive effects and independent effects, and that's when we have more than one agent in the workplace. Occasionally, questions arise concerning the adjustment of an occupational exposure limit for work shifts exceeding the traditional 8-hour workday and 40-hour work week. Since most regulatory and recommended exposure limits are based on an 8-hour workday, the effective exposure for those working 10 to 12-hour work shifts become critical in the fact that the extended work shift means that they may not have the opportunity to eliminate the chemical from their body or reduce their body burden. So it's important consideration to adjust our occupational exposure limits when we're evaluating a person's exposure against either the ACGIH threshold limit value or the OSHA permissible exposure limit. NIOSH, as opposed to OSHA and ACGIH, uses a 10-hour work day. And therefore, we do not need to make adjustments if workers are working 10 hours per day and we're evaluating their exposure against the NIOSH recommended exposure limit. Even if you are evaluating their exposure against the REL and their work shift length in the course of a week is greater than 40 hours, then we would need to make an adjustment. So the easiest way to think about this is if you're evaluating workers' exposures against an occupational exposure limit, either from OSHA, the permissible exposure limit, or for the American Conference of Governmental Industrial Hygienists, the threshold limit value, and their work day is longer than 8 hours, or their work week is greater than 40 hours, we need to make an adjustment to the occupational exposure limit to account for their body's inability to completely eliminate the body burden within the rest period, and that's the period for which they are not working. The rate that a material is eliminated from the body is called the half-life. The half-life is the length of time it takes for the body to eliminate half of the material. Some materials are eliminated almost as fast as they are absorbed. For example, hydrogen sulfide has a half-life of less than 10 minutes. These materials are less likely to accumulate in the target organs. Other materials can take much longer. For example, lead has a half-life of 900 hours, and these materials can quickly accumulate in the target organ if you don't have enough rest time before you're re-exposed. So there's different models that we can use to adjust the occupational exposure limit for these extended work weeks. And so the model that we're going to use here is the brief Scala model, and it maintains the same overall body burden, yet preserves a margin of safety in case workers work again longer than 8 hours per day or 40 hours per week. So what you see on the screen right now is the formula that you would use to calculate a reduction factor. And your reduction factor reduces the occupational exposure limit by a certain percentage. So it's very important that you do both the hour per day adjustment and the hour per week adjustment. If workers are exposed more than 8 hours per day and more than 40 hours per week. If you just do both of the calculations, then you're less likely to make a mistake. It's a very easy calculation wherein the only variable that you adjust for here is time. So this assumes that workers are exceeding 8 hours per day or more than 40 hours per week, and then we're able to use the formula. So we adjust for weekly adjustments and daily adjustments, and then we see which one is the most conservative. So in our example here, we have a workplace exposure to 1,2-trichloroethylene, and the workers are working 12 hours a day, 3 days per week, and the PEL is 10 parts per million. So what is our modified occupational exposure limit for these workers? So what do we need to know? So here is our formula, and for our reduction factor for the daily factor, we realize that they're working 12 hours a day, so we're going to substitute this T for 12 in our formula. And then we see that they're working 3 days per week, so that's 36 hours per week. So in our weekly reduction formula, we use 36. And now I'll pull up a calculator. 8 divided by 12 equals 0.666. And now we have 24 minus 12 divided by 16 equals times 0.666 equals our reduction factor is 0.499. Okay. Now for our weekly adjustment, we have 40 divided by 36. And you can see this value is greater than 1, but I did that on purpose so we can take a look at that. 0.11. And my 36 is 3 times 12. That's where I got my 36. And now for the rest of the formula is 168 minus 36 divided by 128 equals times 1.11 equals a value that's greater than 1, and therefore we will not do that adjustment because we never want to adjust above the occupational exposure limit. This is a very important consideration. We never use it for people who work only 5 hours per day and 30 hours per week. We never adjust up our occupational exposure limit. That's why I wanted to have that in there for you. So now the formula is our reduction factor times our OEL gives us our adjusted OEL. So our reduction factor was 0.499 times the OEL, which was 10, .499 times 10 equals 4.99 parts per million. And this becomes our adjusted occupational exposure limit. Again, I did not adjust for weekly here because we never want to be greater than 1. So now we're going to move on to another method of evaluating exposure, and that is the short-term exposure limit. An STEL, or a short-term exposure limit, is not a separate independent exposure limit, but it supplements the time-weighted average where there are recognized acute effects from a substance. So what I mean by it supplements a time-weighted average is that an STL concentration or exposure is not considered acceptable if the time-weighted average that you calculated exceeds an occupational exposure limit. But an STL may be acceptable. Workers are able to be exposed for a maximum of 4 15-minute STL periods throughout an 8-hour work shift if there are at least 60 minutes between each of these 4 15-minute exposures. And the best way, I believe, to display this is to display it. So here is an example of a worker's exposure. And you can see by looking at the material that there are 2 30-minute periods which a worker is at the STL. So are these STL exposures acceptable or not acceptable? The first step would be to calculate the time-weighted average, and the next step would be to evaluate the interval between these 15-minute STL exposures. So let's start by calculating our time-weighted average, since it's a pretty good review. Okay, so to evaluate our time-weighted average, I threw out sample number 3 and sample number 6 because those were our STEL samples. Now there are times in which you may want to leave them in, but I threw them out because in this example I'm assuming that they were extra samples. So I was sampling maybe with a direct reading instrument. At the same time, I'm taking the personal samples using a sampling pump and sampling media. And then I calculate for each one of those samples the concentration times time. And when I sum all of those together, I came up with a value of 2,770 part per million minutes, because I calculated parts per million times minutes. And now I just need to divide by the sum of time. And when I divide by the sum of time, I come up with 6.44 parts per million. And this is my time-weighted average. So now I can evaluate my short-term exposure limit. So now we can evaluate the short-term exposure limit. The time-weighted average was 6.44 parts per million, which is lower than the permissible exposure limit, and therefore 4 15-minute STL exposures are allowed as long as they have at least 60 minutes in between their interval, and these did have 60 minutes in between, and therefore the short-term exposure, even though it was greater than the permissible exposure limit, is allowed because the time-weighted average has not been exceeded. And this is how we evaluate our short-term exposure limits. Usually we do not combine those samples in with our time-weighted average because we're only taking them for 30 minutes at a time. Other times we can, it just depends on how we sample. So in my example, I threw them out. So we're going to move on to another concept, which is when we have 2 or more chemicals in the workplace. And so we can use either additive effects or independent effects. So if it is reasonable to conclude that the chemicals presented in the workplace could add one to another, and that's because they have the same toxicological effects or they affect the same target organs, then it's reasonable to consider that we can add the exposures together to derive a total exposure. And these are our additive effects. And so an example of additive effects, for example, is something that you're probably familiar with, is that people who are exposed to asbestos and smoke are more likely to develop mesothelioma than those who are exposed to either smoking or asbestos independently. So this is an example of an additive effect. So our formula is very straightforward. It should look similar to you. And what we're doing here is we're just taking the ratio of the concentration that we measure over the occupational exposure limit. And because these are additive effects, we can add them together. And we're looking at whether both of these, when they're added together, exceeds 1. And if it exceeds the value of 1, then we're exceeding the occupational exposure limit. So it's very much like we did when we evaluated an exposure using the severity, when we put the confidence intervals onto an exposure. So here's an example for us. Employees are exposed to the following agents, which all affect the same target organ. We have benzene, toluene, and M-xylene. And we've already evaluated their exposures, and our time-weighted averages are listed here. And so what we'd like to do is evaluate whether the workers are over the occupational exposure limit for the combination of benzene, toluene, and xylene. And so our formula is what we have over what we got. So for let's pull up our calculator here. And so for benzene, 0.1 divided by 1 gives us 0.1. For toluene, 40 divided by 200 gives us 0.2. And now for M-xylene, we have 40, which is our actual time-weighted average, divided by the OSHA allowable, which is our PEL, would give us a 0.4. And when we add these together, 0.1 plus 0.2 plus 0.4 equals a 0.7, which is below 1, which means that if we look at this exposure, and I just multiply by 100, because it's really nice to see that when we're combined, we're 70% of the combined dose when we're evaluating this exposure against the OSHA permissible exposure limit. And we can do the same thing for NIOSH just to look at what the difference would be. So for NIOSH, if we take our 0.1 and we divide it by 0.1, we get a 1. For NIOSH, we'll take our 40 and we'll divide that by 100 and we'll get a 0.4. Oops. And then for M-xylene, we have our 40, again divided by 100, because that's what a NIOSH is allowing us to be exposed to. And now we have 0.4 plus 0.4 plus 1 times 100 equals, we're 180% of our dose. So our last topic is when we have multiple components or chemicals in the workplace, but they are not additive. That means they're independent. So they're not additive because they do not affect the same target organ. And therefore we just simply evaluate each one individually using the formula which I always say is the severity formula, where we take the concentration of what we actually measure and we divide it by the occupational exposure limit for that chemical, and that will give us the total value. And then, of course, if the ratio exceeds 1, then we're over the occupational exposure limit, and if it's less than 1, then we're below the occupational exposure limit. So in this example, we'll use two things that we know affect two different target organs, one of them being toluene and the other one being cotton dust. And so these are the workers' exposures. And now let's go through using that severity calculation to see what we would come up with. So for toluene, okay, so I have the formula here. The total value is the time-weighted average divided by the OEL. For toluene, our time-weighted average was 25, and we're going to divide this by the OEL, which is 50. 25 divided by 50. So we are at 50% of dose. And for our cotton dust, our time-weighted average was 0.1, and we're going to divide this by 0.2. And we are again at 50% of dose. And then we'd evaluate each one of these separately. We may have to put a confidence interval on those depending on how we're doing our evaluation. But now you can see the steps that you take to evaluate chemicals for independent effects, mixture effects, and adjusting the OEL for unusual work schedules. Thank you, and I hope you have an enjoyable day.